Hello everyone and welcome back. So now we're going to be talking about impact, and specifically the energy losses from impact. Last time we talked about that coefficient restitution. We said that the separation velocity after impact is going to be less than, in most cases, than the velocity before impact. Now, if velocities are changing, then you might realize that, hey, the kinetic energy is also going to be changing. And it's not going to be the same. When you add up all the kinetic energy before and after an impact, unless it's perfectly elastic, there's going to be a difference. And that energy can be lost from various things, like heat or sound or due to plastic deformation. If you get a scratch on one of the golf balls you're using or something else, or if it gets kind of bent out of whack, well, energy got stored when that happened. Now, in a plastic collision, that's when the coefficient restitution is 0, when they stick together. The energy lost is a maximum. However, that doesn't mean that their energy goes to 0. If you're wondering why that is, it's simply because even though they stick together, we've got two blocks and now they're stuck together, well, afterwards, they might still be moving as a unit. And so they still have some kinetic energy. It's just the amount of kinetic energy they had before, we've reduced that by a maximum for a single collision. Now, last time we talked about central impact. There were two equations we had, and it all worked well. Now we're going to talk about oblique impact. That's where one or both of the particles' velocities is not along the line of impact. That means there's going to be four unknowns here. Luckily, we have four equations. We still have our first two from central impact. We can just ignore the velocity in the y direction. X direction is usually the one we specify for the line of impact. And say, okay, along the line of impact, we know that momentum is conserved, and we know that our coefficient restitution is going to be calculated from the final and beginning velocities. So that's good. What about the y direction? Well, in the y direction, the momentum of each of the particles is conserved individually. Now, there's some, though I guess that would be conserved as well, but individually they're conserved. So the momentum in the y direction of particle A is going to be the same before and after impact, and the same for particle B. Okay, so procedure for analysis. So in most impact problems, you know the initial velocities of the particles, as well as the coefficient restitution, or at least you can look it up. And we want to find those final velocities. The best thing to do after that is to define your x and y axes. Remember, line of impact connects their mass centers, and that's usually the best one to say that's the x-axis. You make the y-axis if you want to, but you don't have to. So, and normally the plane of contact, that's the y-axis. That's where a plane that is perpendicular to our line of impact. For both central and oblique impact problems, these equations apply. So go ahead and use them. And for those oblique impact problems, remember that the y components of the momentum are constant for each of the particles. So I believe that's everything for this. It is. So next time we're going to jump into our first example. So thank you very much for listening, and I'll see you all next time. Have a wonderful day. Bye-bye.